Hello everyone, I'm Guoliang Kang from the University of Texas Austin. Thanks for inviting me to give this talk. Domain adaptive semantic segmentation is one of the representative tasks learning from limited or imperfect data. It aims to give good cross-domain dense predictions when in-domain annotations are not available. So in this talk, I will introduce our recent work to deal with such a problem. This talk is divided into 4 parts. I want to begin by an introduction to provide some background information. Then I will move on to introduce some previous works in this field. Next, I will introduce our method in detail. Finally, I will give a brief summary about this talk. So let's start with an introduction to the background. Deep learning has achieved great success in various visual applications, such as image classification, semantic segmentation, and so on. So, for example, on internet, deep learning methods have achieved around 90% top-1 accuracy, significantly outperforming the best traditional safety feature-based methods. The success of deep models can be largely attributed to large amounts of labeled in-domain data. So what if we perform cross-domain predictions? Cross-domain predictions means that the distribution of test data is different from that of training data. That is, training data and test data come from 2 different domains. The domain variations may contain the style of images, the shape of object, the context, etc. So as shown in this slide, given a classification task, we may resort to synthetic data to train our model, as the annotations can be easily obtained. However, we are more interested in the performance of such model on the real-world images. Due to the domain shift, the performance on out-of-domain data may significantly drop. So in the example of transferring from synthetic images to real-world images, the model has never seen the style or the context of real-world images, so it is hard for the model to generalize well to such unseen domain variations. The domain adaptation aims to deal with such a performance gap caused by the domain shift. In the conventional setting of domain adaptation, the target of the test distribution is different from the source one. However, the underlying label sets are assumed to be the same. As the domain variations such as the image style or the pose of the object are not fundamental factors to make a correct classification, it is possible to reuse the knowledge learned in the source domain to make the model generalize well to the target. So, as shown in this slide, for the same category of objects, the images look quite different. However, a person can easily classify them into the correct category. This indicates domain invariant features exist. Domain adaptation usually utilizes such domain invariant features to improve the performance on unseen target domains. So why do we need domain adaptation? Why not try to label the target domain data to make the deep models fit well on the target? It is because in practice, it is usually costly and time-consuming to label large amounts of in-domain data. It is also unrealistic to collect and annotate a dataset covering all the domain variations in the real world. So it may be common to encounter the issues of performing cross-domain predictions in the real world. So for the domain adaptation semantic segmentation problem, we aim to deal with the cross-domain dense predictions. Semantic segmentation is one of the core tasks in the computer vision area. It aims to attach the correct label to each pixel in the image. The The outputs of the predicted masks have the same resolution with the input images, which are highly structured and contain abundant pixel-wise relationships. So given the network trained on labeled in-DOM data, we can usually get good segmentation results. However, in practice, when the target annotations are not available, directly using the source-trained model to make predictions on the target leads to unsatisfactory results. So how do we deal with such performance gap via domain adaptation? Next, I will introduce some representative works to deal with such problem. Most previous methods are based on adversarial training, as shown in this slide. The representative work published on CVPR 2018 proposed a method that uses adversarial training to make the predicted masks indistinguishable across domains. In this way, they try to diminish the domain discrepancy on the whole view. Recent years, many methods resort to self-training to boost the adaptation performance. For example, one self-training method published in RCCV 2019 provided multi-granular pseudo-labels for the self-training process. The motivation is that the transferability of different layer features may be different. So they proposed to provide different kinds of pseudo-labels at different resolutions or scales to provide more accurate supervision information during the adaptation process. Within these two general frameworks, many techniques were proposed to further mitigate the domain gap. For example, one of our recent works published in ECCV 2020 aims to select the most similar or representative source images or even the most effective source pixels to benefit the adaptation process. So both the adversarial training based and self-training based methods have some drawbacks. For the adversarial training based methods, they tend to align the feature maps of the outputs globally. The resulting features are not discriminative enough. For the self-training based methods, they usually need good initialization. They usually need the model to be pre-trained on source or adapted on target in advance. During the training, they are sensitive to the noise, and the results usually have a large variance. So here we focus on the domain discrepancy minimization methods, which aims to learn discriminative and domain invariant features. Our method is orthogonal to the self-training method and can be combined to further improve the performance. So in a high level, we try to build associations between target and source pixel pairs. And then we diminish pairwise discrepancy rather than align globally like adversarial training-based methods. As shown in this figure, we provide a new perspective to mitigate the domain gap while exploiting the pixel-wise similarities across domains. We build the cross-domain pixel-wise cycle association and draw the features of associated pixel pairs closer compared to the unassociated ones. Specifically, during training, we randomly sample pairs of images. Each pair consists of one source image and one target image. Then for a specific pixel S1 in the source image, we compute its feature similarities with all the pixels in the paired target image. We select the target pixel T, which is the most similar one to S1. In turn, we compute the feature similarities of the source pixels with respect to the target pixel T, and select S2, which is the most similar one to T. If the starting source pixel S1 and end source pixel S2 come from the same category, the cycle association from S1 to T and that from T to S2 are treated as valid. Otherwise, the associations are not established. We adopt the cosine similarity to measure the feature similarities during building the cycle association process. After building the cycle association, it is straightforward to directly encourage the similarities of associated pixel pairs by increasing the cosine similarity evaluations. However, such way may introduce bias to the adaptation process because the associated pairs come from two distinct images and domains. So their context may not be exactly the same. Thus, we choose to contrastively strengthen their connections. That is, the similarities between the associated pixel pairs should be encouraged to be stronger than other possible pairs. Moreover, we perform the contrast normalization on the similarity metric D before the softmax operation. So in such way, we are able to more safely strengthen the cross-domain pixel-wise connections without introducing too much bias to the training. Because of the domain gap and the association policy tending to choose the easy tagged pixels, the associated tagged pixels may only occupy a small portion of the whole image or feature map. In order to provide guidance to more diverse tagged pixels before cycle association, we perform spatial feature aggregation for each tagged pixel and adopt internal pixel-wise similarities to determine the importance of features from other pixels. Specifically, with respect to the reference pixel, we aggregate the features from all the pixels in the same image. The weight of each feature is determined by its similarity between the reference pixel. Then the feature of target pixel is denoted as a weighted average between its original feature and the aggregated feature. Finally, such features are adopted to perform the association. So during the backward process, the associated tagged pixel can be viewed as a seed, which diffuses the gradient spatially to multiple receivers. The gradient is diffused unevenly. The amount is determined by the feature similarity between the receiver and the seed. So in this way, the gradients with respect to the associated tagged pixels can also propagate to the unassociated ones. This enables more diverse tagged pixels to be regularized during the adaptation process. Given the images from both domains, we forward them through the backbone to get their features. Then we impose the association loss on the features to mitigate the feature discrepancy across domains. However, the feature discrepancy cannot be perfectly eliminated. The classifier or header can always find shortcuts to overfit to the source data and degenerate the adaptation performance. So we also impose the association loss on the network outputs. That is, we also try to build the associations based on the predicted pixel-wise probability distribution. Different to the associations on feature maps, we adopt a negative KL divergence between predicted distributions to measure the pixel-wise similarities. So in addition to the effect of reducing overfitting to the source, the adaptation may benefit from mining multi-granular relationships. The multi-layer associations are complementary to each other, and both of them contribute to elevating the domain shift. So the objective used to optimize our network contains 4 terms. The cross-entropy loss and the lavish softmax loss are imposed on the source data to facilitate the data fitting process. Moreover, we impose multi-layer association loss on pairs of source and target images to reduce the domain discrepancy during the training. Additionally, as the predictions may carry the semantic relationship information, we propose using linear smooth regularizer to encourage the smoothness of predictions and ease the output associations. So at the inference time, we use the adapted network without any association operation, as the aggregated target features are adopted to build the associations between the source ones during the training. It is expected that the distribution of aggregated target features is closer to that of source features. So we perform the same aggregation at the inference stage. We validate our method on 2 standards transferring tasks, that is, transferring from Sensia to cityscapes and transferring from GTA 5 to cityscapes. The Sensia and the GTA 5 datasets are static images, and the cityscapes consist of the real-world images. So we perform adaptation studies on these 2 standard benchmarks. The adaptation performance keeps improving as we progressively added module into the system. This verifies the effectiveness of each module. Besides, we also verify the effectiveness of the contrastive loss and the gradient diffusion module by removing them from the full system. We observe the performance decreases significantly, which verifies the effectiveness of this 2 key components. Compared with previous works, our method shows superior performance on both datasets. Finally, we visualize the masks predicted by our method and compare our method to the source-only network. The masks predicted by our method are smoother than those predicted by the source-only model, and with our method, the pixel-level accuracy of predictions has been largely improved. So finally, I will give a brief summary of today's talk. Generally speaking, we propose a new framework for the domain adaptive semantic segmentation problem. So our framework can be trained end-to-end in 1 stage, and it introduces no additional parameters. Our method exploits abundant pixel-wide relationships to mitigate the domain shift. We verify that pixel-level cycle consistency is effective to build the cross-domain associations. To regularize more diverse target pixels, the gradient diffusion module contributes a lot. And multi-layer association mitigates the domain discrepancy of both features and outputs. All these modules contribute to the final success of our method. So we hope our method can serve as a general framework to ease the future study in this field. That's it from me. It's my honor to be invited to give this talk. Thanks for your attention.